Okay, so other questions before we get started? Brooks?
Should I save space in my notebook for watching the video I missed on Thursday? Serious question. I'm gonna watch it.
Oh, Thursday.
Yeah.
Wow. It's really too bad you didn't watch Thursday's video because, well, actually, watch Thursday's video before next week. Because Thursday's video, we talked about the baryon asymmetry of the universe, and part of that discussion was sort of looking at aspects of the weak interactions that were important for that problem. So we'll revisit some of those issues next week. This week it won't be so urgent. Of course, if you want to know anything about the monster group or what actually looks like drunk,
Probably already done.
what actually looks like after she has had several glasses of water, you should watch
Add a
that
lot of
video.
water.
Wait, did you
But
catch
it really can stand in isolation from the rest of the flow of the course, so don't make room in your note.
I
All right.
don't know if Caroline was caught on video bringing in that bag of Funyuns.
Okay. All right, so anyway, all right, so what we're going to do now is we're going to start moving away from QED. So we've been talking about quantum electrodynamics, and we're going to start looking at the strong and the weak interactions. And as you might guess, things are going to get more complicated. So sort of, I'm going to take some sort of broad strokes at first, and then we'll get into the weeds. We'll probably actually do some calculations on Thursday. I don't know if I'll get as far as a calculation today, but I'll certainly lay out all of the tools that we'll eventually be using. But as we're moving into different interactions, it becomes important for me to say a few words about like how do all of the interactions fit together. And so, first of all, if we think about all of the matter in the Standard Model, we can break it up into three broad categories. Okay. We have and by the way, at the end of this, actually I'm just going to go ahead and start circulating these around the room. So again, if you have not picked up one of these sheets, feel free to take one of these, and then this is another sheet that has the final rules for the weak and strong interactions. So the neutrinos are leptons. A lepton is any of the electron, the muon, the tauon, and all the neutrinos. We kind of separate the neutrinos from the charged leptons because these are neutral, so they kind of behave a little bit differently. But the neutrinos are by far, they're sort of the most, or the least interacting of all of the matter that we encounter in the Standard Model. In fact, there's only one interaction that even touches the neutrinos, and that is the weak interaction. Good call. So in the Standard Model, it's the weak interaction, but all of them feel the gravitational interaction, though technically the gravitational interaction is not part of the Standard Model per se. Okay, so Wolfgang, what interactions do the charged leptons deal with? Or what do they feel? Are they influenced by? Actually, yes, electroweak, but at room temperature, that's broken down to what? Well, take electroweak and split it in half. What do you get? Yes. So these feel the electromagnetic interaction and they feel the weak interaction. Okay, so this is why detecting charged leptons is so much easier than detecting neutrinos, because they actually they feel the electromagnetic interaction. And it's also why they maybe play a more critical role in structure. Okay, it's hard to make a bound state with neutrinos because you know how you can make a bound state with something that only feels the weak interactions. The quarks are kind of the dirty whores of the Standard Model. They like to get it any way they can. They like it electromagnetic, weak, and sometimes when they're in the mood, they like it strong. So they just do it all. Okay, so they like everything. So when you're dealing with quarks, the diagrams that you draw, the processes that you have to think about are considerably more complicated. Okay, I don't want everybody to get lost in those sheets I was handing out. Those are for you to kind of digest later. So typically when we draw diagrams for neutrinos, it's kind of simple because the only thing we have to think about are the weak interaction vertices. For charged leptons, we have to think about 2 interactions, and then for quarks, 3. Now, what I'm saying when I give this list is essentially a direct interaction. That is, if I'm just looking at a vertex into which and out of which comes a neutrino, or sorry, into which and out of which comes a neutrino and its lepton doublet, then that's only going to be a weak interaction vertex. However, what we find is once we start allowing all of the standard model interactions to come into the game, the processes can actually get tainted with other interactions. So here's just an example. So imagine if I was considering a process of electron-muon scattering. And remember, the idea here is that we fill in the bubble with all possible diagrams. Okay, all possible consistent ways of filling this in. Now, if I just handed you a charged electron and a charged muon and I said they scatter, what would be sort of your initial response to what interaction is causing them to scatter? The electromagnetic, okay? Because after all, the electromagnetic interaction between charged particles is something that we're very familiar with. So you might initially draw a first or a lowest order diagram that looks something like this, and of course this is something that we've calculated a gazillion times now. Okay? But it turns out, something we'll learn when we do the weak interactions, that anytime you draw a diagram with a photon, you can actually draw the exact same diagram, but instead of putting a photon in it, you can replace the photon with a weak neutral boson, Z0. Okay? So the electron and the muon can also, part of the contribution to their scattering amplitude comes from the exchange of a weak boson. And we'll learn next week how to sort of do these calculations. Okay? So there you go. We might have expected it at some level because we said the charged leptons feel the electromagnetic and the weak interactions, and there they are. But truth be told, I can also sneak the strong interactions in there. Okay? So you might say, well, how in the world are you going to do that? Well, remember, there are higher order diagrams. And generally, when you start going to higher order diagrams, all kinds of crazy stuff can happen. So one option is that we can have some photons, but while the photons are moving between those two vertices, they might burp out a pair consisting of a quark and an antiquark. Okay? That's a charge 0 particle-antiparticle pair. It can come from a photon vertex just as well as an electron and an anti-electron or whatever you will. Okay, so the way we might draw this with particle identity flow is something like this. Okay? But because we now have virtual quarks in the game, quarks interact with gluons, and so we can now imagine gluon loops being exchanged by the quarks at various positions in this loop. Okay? So the point of this, and you know, technically what I drew here might not be exactly an allowed diagram. You have to be a little bit careful, and we'll understand why today. But technically, the higher order you go, you have to be careful and take into account generally all 3 interactions because they can contaminate these very complicated internal processes for higher order diagrams. Okay? Now this is a very indirect sort of influence of the strong interactions on the scattering process. It's only gluons exchanged between virtual particles. And generally you can expect this is going to have a much less significant contribution to the amplitude than say this, or even this. Okay? Okay, so what we want to talk about today, what we want to start focusing on for this week are the strong interactions in particular. And by this sort of picture up here, if we want to kind of work at the lowest order, that means we're going to have to relegate ourselves to thinking about quarks. Okay? Strong interactions can sort of contaminate diagrams with just charged leptons, but we don't want to consider diagrams that complicated if we could avoid it. So let's just think about quarks and the strong interaction. But if we're going to think about quarks for a moment, there is something we need to keep in mind, and that is that quarks are charged particles. And that means that, first and foremost, quarks can interact via the electromagnetic interaction. Okay, they have electric charge. Now the good news is that to handle quantum electrodynamics with quarks, there's really no change from doing quantum electrodynamics with leptons, like the electron, the muon, or the tauon. The only difference is that the quarks do not carry integer charge. Okay? So generally speaking, everything, and by everything I mean all of the labels like the U's and the V's and the photon polarization epsilons, all of the stuff for quantum electrodynamics and the Feynman rules carries over to quarks. The only difference is the vertex factors, because the vertex factor, GE, secretly carried a factor of E, where for the leptons, this was just the fundamental electron charge, okay? But for quarks, we're going to substitute 1/3 E, or plus or minus 1/3 E, or plus or minus 2/3 E, depending on which quark we're dealing with, okay? And you don't have to remember which quark has which charge, that's why I gave you those sheets, okay? So literally, drawing Feynman diagrams, evaluating Feynman diagrams for quarks with quantum electrodynamics is almost identical. The only difference is that this quantity GE gets factors of 1/3 to 2/3 in various places. Okay. Very, very minimal change. All right?
Alex,
Yeah.
would that only be for vertices with a quark?
Yeah. So what I have in mind is a vertex like this. So this is not a momentum, that's actually a quark. So you have a quark come in, the same quark go out, and a photon leave. It conserves charge, so if this is a 1/3 plus 1/3, it's a plus 1/3 that leaves. Okay. All right, so we obviously want to talk about quantum chromodynamics. So now what we want to do is we want to change this to quarks and QCD, and now it's going to get different. Okay? So let's talk about some of the things that are going to change when we talk about QCD. So first of all, we at some point in the past wrote down the QCD Lagrangian. So let me remind you of what that's going to look like. And I'm going to write this in a slightly different form than what you've seen before. Okay, so I'm summing over the 6 quark fields. There are 6 types of quarks: up, down, strange, term, top, bottom. Each of them is represented by a field. Okay. I don't have to separately include the antiquarks because the Dirac Lagrangian is powerful enough to handle quarks and antiquarks in one go. Yes, Rochelle?
Is the like 1/16 pi times all that stuff like multiplied by 6, or is it not part of the sum?
Sorry, say it again?
Is like the 1/16 pi times all this stuff, is that like multiplied by 6?
No. So this is the, well, I'm not done yet, first of all. This is the kinetic term for the gauge fields. So these are just the Dirac Lagrangians for each of the quark matter fields. There are 6 different types of quark fields. But for the whole process of gauging it, I introduce a set of 8 gluon fields. And that set of 8 gluon fields has this Lagrangian. Now this A goes from 1 to 8. So there's a summation that's happening in here. So technically, in a sense, there's not a factor of 6 here, but really something like a factor of 8, because there's 8 gluons. So this term is for gluons, this term is for quarks. 6 quarks, 8 gluons.
It's not in the sum.
Say it again?
It's not in the sum.
It's not in the sum? What's not in the sum? Sorry, this summation, well, there's no I over here.
Yeah.
So this summation is not doing anything to this term.
But if it was in the sum, it would still be.
Yes, it's not in the sum. This is what I'm trying to say. Yeah, it's not in the sum.
Okay,
It's in the like gluon sum, and this stuff over here is the quark sum.
yes.
So it's not in the sum.
I think I'm getting confused on why you're worried if it's in this. I mean, it doesn't have an I anywhere, so no, it's not in the sum. Is that?
I guess, I mean, it would change things.
So how would I notate it if it were in the sum?
Parentheses on certain things.
Around the stuff.
Parentheses on the stuff.
Oh, I see what you're saying. I see what you're saying. So here, okay, yes, this makes you feel better. There you go. Is that better?
Yeah.
That's good. Okay, all right. Okay, all right. So this term should look familiar. This is what we had in the QED case, but of course we know that QCD is not like QED because QCD is. Okay, Connor.
What's up?
No, actually, Steve-O. Sorry, I'll put Connor's picture up there. Steve-O.
Can you use my full name, please?
Yeah, your name's Steve-O. Oh, sorry. Space Wizard Steve-O. There was a healthy discussion about how we interpreted that picture, by the way, back in the first days of the class. You should find out about that. What is one of the significant differences between the gauge symmetry of QCD and the gauge symmetry of QED?
Well, in QCD, you've got 3 different types of charge.
Yes, you got 3 different types of charge. So if we were going to throw down some like group theory words, what would we say about SU3 compared to U1?
So QCD is SU3,
Which is
non-abelian.
non-abelian, yes, thank you. I thought we'd get to it eventually. Right, the strong interactions based on SU3 gauge invariance, that's a non-abelian group, and that brings in additional terms in the gauge field strength, and those unfortunately take the following form. And my notes are so small, I don't actually know if I'm going to be able to read the indices right, but
Sick. We'll get there at the end of the day.
I have no idea.
Oh, yeah, I don't know if this sounds right.
I think it's necessary.
Nope, it's the bad one.
oh man, that's an E. Yeah, that's an E. Okay. All right, we're almost there. So close. Okay, so there are these 3 additional terms in the gauge field strength for the gluons. But remember, we talked about this when we first wrote down the QCD Lagrangian. Anytime I see a product of fields, that represents an interaction. Okay, so secretly this d mu is just d mu plus ig lambda dot a mu. So the fact that this d mu is multiplying psi and psi bar means that there's an interaction between the two quark fields here and the gauge field a mu. That's the strong interaction, okay, of the gluons interacting with the quarks. Mass terms for quarks, this is just sort of the standard kinetic term. But here we have 3 gluon fields multiplied together, 3 gluon fields, 4 gluon fields. And so what we're going to find is new vertices in the strong interactions of just gluons. And we're going to have from these 2 terms a 3 gluon vertex for each of them, and for this term a 4 gluon vertex. Okay, and if you look on that sheet that I passed out, you'll see the gluon vertex factors. Okay, and these are now new allowed contributions to Feynman diagrams for the strong interactions, and so you can imagine things can get a lot more complicated when you're dealing with quantum chromodynamics. Yeah, Nathan.
Is that a mu in the covariant derivative? Is that like an a mu some a?
Okay, yeah, so sorry. So this guy is secretly this, where these are the 8 generators of SU3. Okay, and I'm going to come back and talk a little bit more about the lambdas in a minute. So the way that we think about this is A mu has space-time dependence. These are a set of constant matrices. They're the 8 generators. But together, it creates sort of a space-time dependent generator. Okay? So, this structure is very complicated. We kind of waded through it when we were doing the non-abelian gauge invariance. Now we're really going to focus more on the consequences for Feynman calculus, so we don't necessarily have to wade back into this in detail. But I will make some remarks to clarify this in a few minutes. Remember, in all of this, any of the psi fields is really secretly this triplet. So the whole point of the strong interactions is that a quark is really a vector in color space, so it can have a red component, a green component, and a blue component. And then SU3 is realized as complex 3x3 matrices that kind of rotate these little 3-component vectors. Okay? So this is very condensed notation. The size, there are 6 of them, but each of them are 3-component. The A's are space-time vectors, okay, but there's really 8 of them. All right, so there's a lot of complications in this thing. All right, so the first thing I want to stress to you, which I talked about when we first saw the strong interactions, but I feel like now is when we really have to drive the point home. When we say that there are 3 charges in QCD, we are not saying that there are 3 different values of the same charge. So in electromagnetism, we're familiar with the idea that there's the positive electron charge and the negative electron charge, and then for quarks there's fractional charges. But those are just different values of the same type of charge. In QCD, there are 3 distinct types of charge, each of which can have different values. Okay? Now the good news is that we only have to think about essentially positive and negative, or color and anticolor. We don't have to deal with fractional stuff. Okay? So there are 3 different types of charge, red, blue, and green. And for the particles in the standard model, each of them takes one of 2 values: red anti-red, blue anti-blue, or green anti-green. Okay? Yeah.
So there's no 0 color charge.
Well, yeah, there is. I'm going to get to that in just a second. Okay? All right. So let's talk for a minute about the interaction with the gluon and the matter field, okay? Because I want to kind of give you a way to interpret this. So from the usual gauge covariant derivative, which is the same kind of derivative we saw in QED, it's just a little more complicated because SU3 is not abelian. We can think about the vertex in QCD in a manner very similar to the vertex that we had in QED. Except this time, instead of a photon, it's going to be a gluon, which is emitted or absorbed. So we represent gluons by a different kind of curve. So generally speaking, that's a photon, that's a gluon, and these are the weak bosons. These are jagged. I'm maybe being a little lazy with my jagged. So when you're looking at diagrams and you see the sort of curvy, that's the photon, springy, gluon, jagged, razor sharp saw teeth, that's the weak bosons. Okay? So I've got a little gluon here. And so far this looks a lot like QED, but it's actually a little bit different than QED for the following reason. In QED, the photon doesn't do anything with charge, right? It doesn't have any electric charge. So in QED, whatever comes in, say if it's an electron, the same thing goes out. Okay? Because of conservation of electric charge. However, the whole point of the strong interactions is that the gluons and the strong interaction itself is changing the color charge of the quark. So what we have to do is, in addition to labeling what kinds of particles we have that are moving through the vertex, we also have to label the color charges. So as an example, we might have an incoming quark which is actually red, so I could put a little R to label that as red. And then through this interaction with this gluon, the outgoing quark might be blue. Okay? Now based on that, there's 2 ways to interpret what this gluon is. One way is to think about the gluon as something moving into the vertex. And if it's moving into the vertex, then it has to carry something that cancels the red, that gets rid of the red. Well, what do you think gets rid of red? Anti-red. And then it has to give you the blue. Another way to interpret it is if the gluon is moving out of the vertex, I want to carry away the red, but I have to cancel the blue. Okay? So which way you want to interpret this flow, okay, is going to determine the labeling here. Now, to be clear, we don't have to be that careful because this particle is the antiparticle of this particle. So really, when we draw the diagram, when we have our little gluon springy thing, all we have to do is put an arrow on it, and that immediately tells us what's happening with its color. Now, we're free to pick the arrow going away or going towards. It's just if we pick it one way or the other, we have to realize what the associated color labels are. We don't have to do that with the photon because the photon is its own antiparticle. It wouldn't matter if you drew it up or down. Okay? But gluons are distinct from their antipartners, and so we have to put an arrow on the gluon line to distinguish which one we're going to think in terms of. Again, you could do it either way. It doesn't matter. Okay? Does everybody understand this point? So one of the things that's nice about this is it allows us to think of gluons as something which carries color and anticolor. So gluons are sort of bicolored. They're always going to have two color factors associated with them, one color and one anticolor. Okay? And if you think about it, if you look on the sheet of particles, there's something else in the standard bottle that kind of carries that same structure. What is that? Don't look at the one I gave you today, look at the first one I gave you. What else carries that sort of color-anticolor structure? Say it loud. Mesons. Okay? So mesons are two quark bound states, and they always come in quark-antiquark pairs. So mesons carry color-anticolor. All right? So mesons, which are matter, they're quarks, and gluons both have this sort of color-anticolor structure. Okay? So it's actually worthwhile to take a moment to look at, well, what kinds of color-anticolor states should we be considering? And it turns out that there's two categories that are distinct for obvious reasons. First of all, there are what are called the octet states. And so the octet states we can enumerate as follows. And as per octet, you can imagine there's going to be 8 of these.
Are those cats? Is that how you write them?
Yeah, you can think of them as cats. They're states, so yeah, you can think of them as cats. Maybe lose my place, Brooks, and we'll show you. Okay, there we go, never mind. You're safe for now. Ask another question though when I'm coming over there.
Spencer, you should
It's not going to end well.
What's the inner product?
Easy, buddy.
Spencer. Don't get me
Is this in
started.
bottom space?
Don't get me started.
Is this,
I don't like that word.
Are they identical?
Okay. Say it again?
Any reason they're in that order?
No, not particularly.
Somebody decided it.
Okay, so here's the way that we would say this. Color anticolor space is essentially, in this context, an 8-dimensional Hilbert space, and these are just 8 linearly independent basis vectors in that space. Doesn't matter what order you write them in. Okay, and then the good news is that the second category is a loner called the singlet. And the singlet, which we sometimes, just to complete the list, is called the 9th, is just 1 over root 3 red, red bar plus blue, blue bar plus green, green bar. Okay, so first of all, if you ask yourself, if I'm going to allow myself to enumerate all of the color anticolor states, and there's 3 colors, and hence 3 anticolors, how many states, how many pairs do you think I'm going to be able to write down? Just naively. Say it louder. 9, right? I could write down like red, red bar, blue, blue bar, green, green bar, and then I could go and make this a red, blue bar. So, of enumerating all the pairs, there's going to be 9 states. So you might say, well, why do we do this complicated thing? Well, first of all, this is a much nicer way to label things, because when we look at diagrams, it's nice to label this as a red and this is a blue, and therefore this quark is a red bar blue, okay, which is one of these, but it's none of these, okay? The problem is that if you enumerate all 9 pairs, in this notation, it's very, very hard to figure out how things get transformed into each other, and in particular where the invariant state is. In this representation, it is very clear that this is invariant under SU3. It's a lot like the length of a vector in 3 dimensions, and then you do rotations. So think of this as the x component squared, the y component squared, the z component squared. You can rotate all day long and it won't change. Okay? So this particular combination is invariant under SU3, while these are rotated into each other under SU3. Okay? That's harder to see if you just enumerate all the pairs like this, Spencer.
Except for the last one, or including 8?
Including 8. This is not invariant. It does have red, red bar, blue, blue bar, green, green bar, but it's not, they're not all equally weighted. Right? If I took the x component of a vector squared, added the y component squared, and then added 3 times the z component squared, that's not invariant under rotations. Okay?
Shouldn't there only be like 8 basis vectors in SU3, since we have 8 degrees of freedom?
Well, I'm going to get to that in just a second. I'm going to get to that in just a second.
So you just said that was 8 linearly independent basis vectors for this one.
Hold on, I'm going to identify what these are useful for in just a moment, and I think I'm going to reconcile those questions.
Why is that green special in the 8th state? I don't get 2.
I just start writing some of these down, and then I want to flesh out all linearly independent combinations. It's at a certain level, I need to be able to get all 9 of these from the 9 of these. Okay? And yeah, I mean, so to a degree, the fact that this looks wonky is tied into the fact that this one looks wonky. But some of them have I's, some of them don't, some of them have a minus sign, some of them don't. So, this has 3 terms, so you think it's especially weird. But these all have, subtle differences. Okay? Now here's the important observation. All of these, and by the way, you can immediately see how to reconstruct these as linear combinations of these. So for example, if I wanted to construct RB bar, I could just take a linear combination of these 2.
Yeah.
Okay? So I could ask you to construct any one of these as a linear combination of these states, and you could do it. All right? So there's an isomorphism between these 2 bases. All right, so what is important is, first of all, this observation that these are transformed into each other under SU3, and this is invariant. Now, in terms of the physics, what we discover is that all mesons are color singlets. So if I say here's a pi 0 meson, and I'm going to switch between meson and meson because I can never commit. If I hand you when I say meson, it sounds like very like self-absorbed. It's a meson. But when I say meson, I'm like, man, that's weird. It's like mesa. I don't know, it's weird. Anyway, so if I hand you a pi 0 meson and I say, what's the color state? You should just write this down. Okay? This is what we also call colorless. So in answer to your question, Jacob, it's colorless because it's invariant under SU3. It doesn't get changed by the strong interaction, okay? These are what we would call the colorful states. The importance of the colorful states is that these are the various basis states in the Hilbert space for gluons. Now it's important to recognize this because remember when I said we can think of gluons as color anticolor? Yeah. Well, if you stopped there, this would lead you to conclude that there were 9 gluons. Right. Because if I think of gluons as color anticolor, I can write down 9 color anticolor combinations. Okay? But this is not the right answer because SU3 has 8 generators, not 9. It turns out that these linear combinations of color anticolor are the 8 gluon generators. This particular color combination does not exist as a gluon. If it did, okay, first of all, if a gluon existed with this color assignment, we would not be dealing with SU3, but rather we would be dealing with what group? Gauge. If I take SU3 and I add in one more generator that's kind of like really nice and symmetric and diagonal, what group do you think I get? U3, yeah. So if I had a gluon with this color structure, the gauge group would actually be U3. Well, you could ask, like, well, do we know? Is that? Well, it turns out that if you had a U3 gauge theory, this boson would act exactly like the photon. But we don't see that. Okay? So this is experimentally ruled out. There is no gluon that otherwise behaves like the photon. So we know this doesn't exist. We know that one of these is gone, and the residual gauge group is SU3, described by these 8 gluon states. Ariel.
Why is 8 colorless or have color? It seems like if it have the red, anti-red, green,
Yeah, I know. So when I say that something has or doesn't have color, what I'm referring to is whether it is invariant or not under an SU3 transformation. Yeah, I know. Sadly. Okay. Yeah.
So this is saying that gluons always change the color of quarks.
Yes. Yeah, that's kind of the. It's kind of the. So the photon doesn't change the charge of the particles coming into and out of the vertex. If a gluon existed like this, it would behave like the photon in the sense that you could have a quark with one color come in and a quark with the same color come out and then emit one of these gluons. But we don't observe any kind of interaction like that. We always observe that when there's a gluon in the game, it's changing the color of what comes into the vertex and what comes out. Now, I should be honest, I'm going to draw a lot of diagrams like this, where I assign a color and a color here. But if we're really honest with ourselves, we should be always working with these linear combinations. Okay? And we'll see how to kind of get that into the machinery when we start writing down the Feynman rules. Okay, and by the way, just to kind of reiterate the point, the idea that the gluons are bicolored, we could have actually seen up here in the definition of the covariant derivative, because we had this lambda dot A. And what you might or might not remember is that this lambda secretly carries 2 color indices. Okay? And then it also carries a label for which gluon or which generator I'm talking about, and then similarly the A would carry a label for which generator. Okay? So the generators of SU3 are 3x3 complex matrices. So as a matrix, it has 2 indices, and those are color indices. So just in looking and thinking about the matrix structure of this, we could have identified that it was a bicolored object. Okay, so now we're going to do a sort of comparison of the Feynman rules or certain structures as they appear in quantum chromodynamics compared to quantum electrodynamics, which is something that we've gotten kind of comfortable with, and then we'll turn to some calculations. So let's just set up a little chart that's going to navigate us from what we've seen to where we are. So I'm going to consider 3 theories. For each one, I'm going to write down the external states, the internal propagators, and the vertex factors. Because we know that these are 3 of the important quantities that we write down. So once we've drawn a Feynman diagram, we go through and we write down an external state label for each external leg. Anytime we have an internal particle, we write down a propagator. And then anytime we encounter a vertex, we write down a vertex factor. And then there's kind of ways that we get the ordering right by following flows, et cetera, and that's going to be important here too. So the first case is actually the first theory we thought about, which was the ABC theory. Okay? So for the ABC theory, there wasn't a gauge theory. Remember, it was 3 scalar fields, and then I just wrote down an interaction that looked like this. I just said, let's have an interaction where I have a product of all 3 of them, and then we said there's a vertex, and well, I'll just write down the vertex here. So the vertex looked like this, and the vertex factor was just minus IG. Okay? But we did not write down this Lagrangian based on a gauge symmetry. Okay? One of the consequences of that is that there's no notion of conserved charge. All right? So these external particles in the ABC theory, they have no charge that I have to specify. They're their own antiparticles. And moreover, they're scalars. There's no spin state that I have to specify. So that makes the external state labels very, very easy. There are none. There's nothing I have to specify except, is it an A, is it a B, is it a C? Okay? For the internal propagators, these were particularly simple. Okay, because they're just scalar fields. And so that is pretty much it. That's all we need in order to start writing down expressions for M after I've drawn a diagram for a process in the ABC theory. And remember, to draw a diagram, all you do is combine a bunch of these vertices. And remember, you have to have an A, a B, and a C on your vertex. You can't make like 2 A's and a B. Okay. All right, so then we matured a bit, as evidenced by last Thursday, and we went to QED, and when we went to QED, several things changed, okay? First and foremost, it's a real theory. It's describing real matter, which means we have spinors. That means that when we talk about the external states, they have spin degrees of freedom, and so that's when we have to start labeling the external states for matter. And then we also, even though we haven't done very much with this in the homework, we also have to label external states for the photons. And if we encounter an internal matter particle, its propagator is a little bit more complicated than what we saw in the ABC theory. Okay, in particular, whereas this factor was a scalar, this factor is what kind of object?
Matrix.
It's a matrix in spin space because this Q slash, remember, is secretly gamma mu, Q mu. And the gammas are matrices in spin space. So the propagators are spin matrices. The external labels here are spinors. Okay? And then, of course, these are vectors in space-time. All right? So we're introducing more complicated structure. If we encounter an internal photon, then it gets a vertex factor, or sorry, an internal propagator like this. And then we know that everything is built off of the fundamental QED vertex, which looks like this, and that gets a simple factor of IgE gamma mu. All right? And one of the things that we notice in the form of the vertex factor that we did not have to notate here is the notion of charge conservation. Okay? Which is sort of captured by the flow of the matter field. So if an electron comes in and an electron goes out, the photon has no charge, electric charge is conserved. Okay? And that's because this is based on a gauge principle and there's an associated conserved charge. All right, boom, QCD. It's going to get worse. It is going to encompass everything from QED, because we still deal with spinors. Okay? Quantum chromodynamics is a theory of charged particles. It's just its color charge. So it's 3 different charges. Instead of a photon, there's 8 gluons. Okay? So it's going to have a lot of the same structure, but just more complicated. So here we go. When we have external quark states, we're going to not just have to specify their spin state, but we're also going to have to specify their color state, which right now I'm just going to call C. All right, and then if I have an anti-spinor or an antiparticle coming in, I'll have a U-bar C dagger. Now I'm going to write down a lot of things, and then in a few minutes I'm going to come back and show you exactly what each one means. So I'll come back to what these C's look like in a minute. And then we have a VC and a V-bar C dagger. If I have a gluon, it's a vector in space-time. It's described by an A mu field, same as a photon. But the gluons carry color. In fact, they carry bicolor. Okay, so we're going to label the gluons with something that I'm going to call A alpha, and I'll come back and tell you more about A alpha in a minute. And then similarly, if I have an anti-gluon, I can label it as such. If I encounter internal quarks, they're going to get propagators, which fortunately don't look any different than the internal propagators from QED. The propagators don't have anything to do with interactions. The propagators are only, I have something that's moving through space-time. It's got some energy and momentum. So the only thing the propagator really cares about is whether you have spin. You're a little bit more complicated if you have spin, because spin is part of your energy and momentum. Color doesn't really affect the propagator. Okay? You can just happily go through an internal part of a diagram, no matter what color or whether you don't have color, and your propagator really won't care. And then for the gluons, we do have to be a little bit careful to get vertex factors to match up. Okay. And then we are aware that now we have not 1, not 2, but 3 different types of vertices in the strong interactions. Okay, so first of all, we have the analog of the QED vertex. Okay, and it's important to remember that when you draw a gluon, you have to put an arrow on it. It doesn't matter which way you put it, but you have to put an arrow on it. Okay? You don't put arrows on the photons because they're their own antiparticles. It wouldn't mean anything. We have now this 3 gluon vertex. And I'm going to have to do some labeling for this one. So, oh my God. So I'll come back and explain what some of this means in a minute. Beta nu, lambda nu. I'm going to call this an incoming momentum K2, an incoming momentum K3, and an incoming momentum K1. Okay, so let me just write down these two factors, and then I'm not even going to bother with the other diagram. The other diagram, in case you don't remember what's up there, is the 4-gluon vertex. And for reasons which you are about to appreciate, I'm going to spare you writing that one down. Okay, it's in the notes. You can look it up. So first of all, let's start with this one. This is obviously the most important QCD vertex because this is how gluons affect quarks, right? So when we encounter a vertex of this form, we're going to write down minus IGS, where GS is the strong coupling, over 2 times lambda alpha gamma mu. Okay, and again, I'm going to come back and talk about those various factors in a moment. If I encounter a 3-gluon vertex, I'm going to write down a factor of the following form, minus GS squared, or no, sorry, minus GS, F alpha, beta, gamma. And this is implying that I have this particular assignment of labels. Eta, mu, nu, K1 minus K2, lambda, plus eta nu lambda K2 minus K3 mu plus eta lambda mu K3 minus K1 mu. Yeah, so I just want you to just pause for a minute and think about how ugly this one probably is. Okay, I'm not even going to label it, it's horrible. All right? Yeah, it's on the sheet. Sorry, yeah, it's on the sheet I gave you. Sorry, I don't know what I'm thinking. Yeah, Wolfgang.
Is one of those pairs, like lambda, mu, is that supposed to be gamma for lambda?
Sorry, say it again?
You have 2 nus. You have a K3 nu and a...
Oh, a lambda nu, beta nu. Yeah, alpha mu. Yes, you're probably right. Alpha, beta. Yeah, that's probably a gamma. One of these is a gamma, you're right. The lambda, yes, sorry, alpha, beta, yeah, this should be a gamma min, sorry. This is so tiny on my paper at this point, I can't read it. Okay. All right, so fortunately, you'd have to be looking at pretty higher order diagrams to worry about encountering these, but they're going to have their own significance for reasons we'll talk about later on. Okay, but most of the calculations that we're going to focus on are largely going to be geared around just the simple QCD vertex. Yes, Allie?
I thought the question was that there's 2 nus. Is that going to be an issue? Or like...
Oh, sorry. Yeah, so basically I want to pair one of these with one of the 3 here, and so you're right. So I've got mu, nu, and lambda, so there you go. Yes, well.
Should we be worried that it almost looks like that's violating conservation of momentum? Because you have momentum going in and negative momentum coming out? Fine. You're acting on the right.
No.
Okay.
No, because remember when you do a diagram, the only time you really care about momentum and getting the flow right is in external particles. It's very easy to draw a diagram where you end up with all the momentum going in. What you'll do though is you'll write down a delta function that'll look like this. And then that's going to impose that the total momentum is conserved at the vertex. So one of them will be negative. Okay? I mean, look, you could switch the sign of this one if it makes you feel better, but then you have to go in and you have to change the sign in front of K2 everywhere. Okay? So what I'm saying is, this expression is intrinsically tied to this labeling. You can't just arbitrarily write something down. Okay? All right, so to finish, what I want to do is talk a little bit about the various factors that you see here, and then when we come back next time, we'll actually see how some of the calculations with this comes about. So there's quite a few things in here. Let's start with C. So there are 3 colors in QCD. So color space is spanned by, and we can just take 3 simple vectors. Okay, to span the basis in color space. This would be the red basis vector. We'll take this to be the blue and this to be the green. So what I'm saying is, in a calculation, if you want to say I have an incoming red quark, I would write down a UC, and with my C, I would put 100. Okay? Or if I was trying to say I have a red anti-blue plus blue anti-red times 1 over root 2, I would do 1 over root 2 this, and so forth and so on. Okay?
What about anti-colors? Are those like negative?
So the anti-colors, yeah, so the anti-colors are going to be the daggers.
Oh, I see.
Yeah. Okay, so generally a color state is a linear superposition of these where the coefficients can be complex, obviously. Okay? That's why when we talk about the anticolor states, we want a Hermitian conjugate. We don't just want to transpose, but we also want to take the complex conjugate. Okay? Now, again, when we do calculations, we're actually going to put in the vectors and we're going to manipulate them so you get a little more comfortable with it when we actually do some calculations next time. Okay, so that's what the C factors are where you see them. They're just labels for the colors of the external quarks and antiquarks. And then we have the A factors. And where do my A factors appear? Well, they appear here. Okay. And the A factors are labeling the 8 gluons. And we can think of them as the following. Literally, we can just do an 8-dimensional Hilbert space of gluon states, and then just do A1, A2, etc. Okay? So when we want to specify which of the gluons we're talking about, now I will go ahead and say this, it's very rare that we do a process that has an external gluon. You can do it. I mean, in fact, so far, I don't think I've given you a single QED calculation with an external photon. Although you can certainly do QED calculations with external photons. It's much less likely to encounter a QCD calculation with an external gluon. Okay, because gluons are not long-lived particles. We don't have free gluons. But at any rate, if you needed to do a calculation, you would have to specify which gluon you were talking about, and that would be what the label A alpha was giving. And then the last thing we see in this mix are the lambdas. Here. Okay. So the lambdas are probably the most complicated part of this story. Oh, sorry, there are 2 more things that we see. So the lambdas, so first of all, the lambdas are, if I'm honest about it, they carry not just a label alpha, but they also carry 2 matrix indices, I and J. So these are color indices, and this is a gluon label. So let's remember what the lambdas are. They are the generators of SU3. Each of them is a 3x3 complex matrix, and there are 8 of them. So this alpha is telling you which of the 8 you're talking about, and the I and J are the labels of the 3x3 matrix. Now it's a 3x3 matrix because it acts on color space, so those labels are color labels. Okay? These each take values 1 to 3. This is which of the 8 gluons you're talking about. So the label alpha goes 1 to 8. All right? Now, just like with spinors, because we get lazy, we are not going to explicitly label the color indices, which means that order is going to be important. We're going to rely on matrix multiplication. Now, when we're creating singlet things, things that have no net color, that means we're going to be combining these C's and C daggers with these lambdas in the same way that we make spinner sandwiches, right? We take a spinner and a conjugate spinner, so we have like a U bar and a U, and then we stick a spin matrix in between. Here we're going to have a color, a Hermitian conjugated color. Those are kind of the bread of the sandwich, and then we're going to have factors of lambda and other color matrices in between. But at the end of the day, when we multiply it all out, it's going to be a number. Okay? And again, we'll see that in the context of calculations. So these are similar in many ways to the gamma matrices. The gamma matrices connect spin space, which is referenced by I and J. They go 1 to 4, but it's not 1 to 4 of space-time, it's 1 to 4 of spin space. They connect spin space to space-time. Here, the lambdas connect color space to gluon space. Okay? All right, and then the last thing that we see are the F's. And what are the F's? Yeah, the F's are the structure constants of QCD. They're the things that appear here specifically because QCD is non-abelian. Okay? QED was abelian. What were the structure constants? Where do the structure constants arise? Where do they appear? They're the right-hand side of the Lie algebra. Okay? If the group is abelian, everything commutes, so this side is 0. That means the structure constants are 0. So for QED, the F's are 0, and indeed, in QED, none of these terms appear. You just have this term. For QCD, the structure constants are not 0, and in fact, you worked with them in homework 3, I think. I gave you the structure constants for SU3 back then. This is where we actually use them in particle physics, okay? And so they're going to enter into vertex factors if we encounter vertices of 3 gluons or even 4 gluons, okay? All right, so that's all we're going to do today. There's an additional technical complication that comes in when you have internal loops of gluon lines, but I'll mention that to you next time. So we'll see you on Thursday. We'll do some calculations.
Oh, there it is.